Okay, section 12.5, logarithmic functions. So this is going to be very similar to 12.3. Also, I guess I should say right now we're clearly skipping 12.4. 12.4 is an applications section that, given what's happening this semester, I don't want to devote too much time to because we're going to have enough things to keep us busy for the rest of the semester anyway, so we're skipping 12.4. So 12.5, logarithmic functions. As I said, this is going to be similar to 12.3 where we studied exponential functions. And then in the next section in 12.6, we'll be looking at the link between logarithms and exponentials in a much more in-depth environment. So we have three things to talk about here. Number one is we're going to just briefly touch on moving between logs and exponentials. So this is the basics of how we go between a logarithm and an exponential. As I said a second ago, in 12.6 and 12.7 we'll be investigating that further. We need to look at how to solve log equations. And finally, we're going to be looking at how to graph log functions. And the graphing, just like in 12.3, is not going to be very in-depth because, as you'll see when we get there, if you understand how to graph an exponential, which we did in 12.3, you understand how to graph a logarithm, which is nice. So, logarithmic functions. Functions. So the basics, the terminology, f of x is log base b of x. So the way that we read this is exactly as I just said it. It's log base b of x. X is not an exponent. X is an argument. So a lot of times you'll see this written as log base b of x, like this, in parentheses. We tend to drop the parentheses unless it's a multiple term, like a binomial or trinomial in that argument, which we'll see. But the b is a subscript. It's not a full number, so this isn't b to the x. It's log base b of x, the whole thing. And if y equals log base b of x, b must be greater than 0, and it can't be 1, then x equals b to the y. So this is the primary way that we move between logarithms and exponentials. You can see that our logarithmic function is the exponent in the exponential, and the solution to the exponential expression is the argument of the logarithm. So they are linked this way, so when you solve a logarithm for a value, you are finding an exponent, so to speak. So let's look at a couple examples that highlight this a little bit more, so we can get a little bit more comfortable with it. So we're going to look at 3 log base 5 of 25 equals 2, log base 6 of 1 over 36 equals negative 2, and log base pi of x equals 4. So when you are switching between, it is a two-way street, so to speak. You can go from logarithm to exponential, and you can go from exponential to logarithm. So a lot of times we solve our logarithms by going to the exponential because we understand exponents more than we understand this weird logarithm thing. And so using our format here, Log base 5 of 25 equals 2 says that 5 squared equals 25, which we know that's absolutely true. That's what 5 squared is. That's kind of the way that you want to think about logarithms is convert. You can either do it on paper or in your head as you feel more comfortable. Convert to that exponential and see, do I have a true statement or not? So for this next one, this is 6 to the negative 2, according to this equation, equals 1 over 36. And that, again, is true. 6 squared is 36. Negative pushes it to the bottom, 1 over 36. And then finally, this says pi to the 4th equals x. And this is also true because x is a variable. So in this case, you would be finding out what x is, which is what we've done here. So we can use this switch between these two to solve an equation that has a logarithm. So let's look at two examples of those. So we are going to solve the following. So in part A, we have log base 3 of x equals 4. And in part B, we'll have log base b of 1 equals x. So in part A, switching to our associated exponential, our base is 3. It's 3 to the 4th equals x. And so x equals 3 to the 4th is 81. So that's how we solve a basic logarithm when you're trying to solve for the argument and solve for x. Switch it to your exponential and evaluate. Now for this one, this is saying b to the x equals 1. So now we're asking ourselves what power of b will give us 1. And we know that anything raised to the 0th power will give us 1. So we're going to do more solving of equations in a bit here. Evaluations, and again in 12.6 we're going to be really diving into solving equations and both evaluating exponentials and logarithms. But I just want to talk about 3 properties of logarithms right now that will make our life a lot easier. Properties of logarithms. Actually, I have 5 right now. So we're going to add a couple more to these rules in the next section. But for now, these will help us in this section, just focusing on logarithms. So number 1 is this part B that we just did. Log base b of 1 is always 0. And this is true no matter what our b is. If it's 7, if it's 3, if it's 1/25th, if it's 1/9, if it's 7/16, anything base to argument being 1 in the logarithm is equal to 0 because anything raised to the 0th power is equal to 1. And along with that, log base b of b will always be 1 because anything raised to the 1st power, b to the 1st, is equal to itself. So these are 2 properties or answers to logarithms that you should know. Oops, this should be a 3 now. The next one is b raised to the log base b of x equals x. So this is a weird one. So this whole thing here is in the exponent. But the idea is if we were to switch from this exponential to the logarithm, this would be log base b of x equals log base b of x. Because we take the base, we raise it or we put this inside the argument of the logarithm, and then we set it equal to the exponent, which is this. And if you're looking at this log base b of x equals log base b of x, this is always true. It's just like saying 1 equals 1. This is just always going to be true. And similarly, property 4 here, log base b of b to the x also equals x. So again, if we switch this back to its exponential from its logarithm, we have base b to the x equals the argument b to the x. And again, this is like saying 1 equals 1. This is just always true. And so these are useful properties when you're evaluating logarithms or simplifying logarithms. And the last one, log base b of 0 is undefined. So we will never have we don't have any power that will ever get us to 0, no matter what our base is. That's the idea here. So I have some practice problems that I would like you to try. So again, like we've been doing, pause the video and try these out. So we're just evaluating. And this is just getting you some practice using these properties here. So we have log base 3 of 3 squared, log base 7 of 7 to the negative 1, 5 to the log base 5 of 3, and 6 to the log base 6 of 13. So use your properties here, pause the video, and get your answers. And I'll start going through them now. So this, log base 3 of 3, we are in this scenario here, so this is equal to 2. This one, we're in the same scenario. This is equal to negative 1, 7 to negative 1, right here. This one is property 3, 5 to the log base 5 of 3, so this equals 3. And this one here, again, same property, 6 to the log base 6 of 13, this equals 13. So fairly straightforward. Just want to get you some practice using those properties so you can see how they work with numbers. Now the last thing in this section is the graphing. I know it's very quick, very short section because we're going to be doing a lot more in 12.6. So we're going to be doing some graphing of logs. So just like with the exponentials, we have some properties of logarithms properties of their graph, not like these properties, that allow us to graph it really quickly. So if f of x equals log base b of x, where b is greater than 0 and strictly not equal to 1, number one, f of x is 1 to 1. Remember, that means it's invertible and passes the horizontal line test. The x-intercept is always 0, 1. The y-intercept is non-existent or doesn't exist. Up there. our domain is 0 to infinity, so we don't plug in negatives into a logarithm. And our range is negative infinity to infinity. So even though we don't plug everything in, we still get all real numbers when we get our answer to logarithms. And this always includes the points b, comma 1, and 1 over b, comma negative 1. So just like with the exponentials, we have 3 points that we always have, and if we remember these 3 points, no matter what our base is, we can graph a logarithm. So if we take a look at our graph, since our domain is 0 to infinity, I don't need to worry about negatives. And I'm going to put a 1 here, a b out here, negative 1, positive 1. So we always have 0, 1. We always have b1. And then we always have negative 1, 1 over b, which I'll put like here. 1 over b, comma negative 1. And our graph does this. This is b, comma 1, 0, comma 1. Oops, not 0, comma 1, 1, comma 0. I wrote this incorrectly. 1, comma 0. My goodness. And then this point over here is 1 over b, comma negative 1. And this is f of x equals log base b of x when b is greater than 1. So just like with exponentials, we have 2 different graphs for logarithms. One when b is greater than 1, and since b needs to be greater than 0, one when b is between 0 and 1. So our other graph that we could have, something like that, negative 1 and 1. It's the same, except now our b is going to be between 0 and 1, which means b is here, and this out here becomes 1 over b. So the points kind of flip-flop. We still have 1, comma 0, just like we did here. And now b1, b comma 1 is here, and 1 over b negative 1 is out here. And then our graph does this. Oh no. That was a horrible graph. Very, very terrible. So this is still b comma 1. This is still 1 comma 0. This is still 1 over b comma negative 1. And hopefully your graph looks better than mine does. Right, but that's the idea, is we have 2 different versions. One when b is bigger than 1, one when b is less than 1. Just like we did with exponentials. And so if we were to graph something, graph an exponential, we just double check what situation we're in. So let's say we're going to graph f of x equals log base 1/9 of x. Well, our b is between 0 and 1. So we're going to be in this situation. So when I set up my axes, I'm going to have 1. Now here I'll put 9. And that means in here is 1/9. This will be 1 and negative 1. So we always go through 1 comma 0. We always go through b comma 1. And we go through 1 over b comma negative 1. And then I'm going to cheat a little bit and turn this so I can graph it better. It'll look like this. This is 1/9 comma b, oops, comma 1. This is 1 comma 0, and this is 9 comma negative 1. And this would be our f of x. So as long as you can memorize the points from these two versions, just like in 12.3 for the exponentials, graphing these becomes relatively simple. So this is a pretty quick one, but this is the end of 12.5. In the next section, we'll be solving lots of equations, simplifying a lot of logarithms and exponentials, and diving into the properties between them in more depth.